Wow, this is a pleasure. Thank you so much for taking your time to join me here, to join us here. Actually, these are two consecutive talks. And for you online, for joining also. And thank you, Fanas, for having us. This is an absolute pleasure. Sorry for starting with a slightly different title. I was thinking what would be like a tease towards the weird space that we inhabit that is somewhere between technological tools and systems and algorithms, but at the same time, very much humane focus, at least what we try to do. So this is me, as Fanas said. I'm from ICDCA, the Department for Computing in Architecture at the Stuttgart University. I'm also a PhD student at the Max Planck International Program for Intelligent Systems. A bit about me, I feel like this was covered, but maybe some things that we will address, the two of us today, is how weird it is that architects are actually exploring these highly technical and technological spaces, and how to do this from a humanistic perspective, if you will. So I feel like what brought me here as an architect, as a designer, as a researcher, as a technologist, I guess, all build towards this conjoined effort to try to make technologies accessible and open for diverse participation. And I guess I just need to minimize this one. So I work with, is this working? Thank you, previous. I work with cobots and AI, and my research interest is with close human-robot collaboration. And it's supported by sensors and machine learning, and it's tested for accessibility for diverse people. And diversity could mean many things. It could mean different bodies. It could mean different cultures and languages. And that's very cool for me, but how is this relevant for architecture? I wanted to bring you kind of up to speed with the discourse that is taking place at the ICD. And the focus of all of our research projects are the key challenges in prefabrication and construction. So when we're talking about design research, our motivation is addressing the key challenges in fabrication, their processes and their designs. So we look towards our built environments as an ongoing design challenge because of its pollution, because of its energy consumption, because of its CO2 emissions. And thinking about this, we look towards improving on all of these points that were already identified by the UN as early as 2022. This year is significant because it was right after COVID. So we stopped polluting for a moment there, and then we went back at full speed, if not more. So we have a strong need for sustainable architecture and manufacturing, from production to emission to type of materials that are used, component life cycle, building energy cost. All of the reviewers agree that we need to rethink our architecture and fabrication processes and products. At the same time, the demand for housing worldwide is growing. So while you see 1, 2, 3, and 4, you think to yourself, well, you should stop building altogether. And it might help, but at the same time, we have to, because we need to answer to the greater population need. At the same time, we have this as a challenge. So concurrently, we have a major shortage of skilled workers and high employee turnover, which leads to low productivity and quality. We have people working in the construction site and staying there. The average is like 3 months, and then we have new people coming in, and they need to learn new tasks. And so the industry struggles to meet increasing demands for new buildings. The response initially was this idea that is called Industry 4.0. It's an initiative that embraces technologies like cyber-physical systems and robots, and the idea is to boost profit and optimize production chains. This is the source. The source is the automotive industry, where most of these robots come from, as early as the 50s, actually. But automation implementation, unlike what we see in this video, in the construction industry is not done in a clear production line, in a closed, controlled environment, which means the automation of our practice is far more complex. We need to rely not only on the knowledge of professionals and tacit knowledge, but also to respond to constant changing conditions, from illumination to ground level changing to rain to everything. And so while the European Commission declare this as a good idea. Actually, the implementation is really, really hard, which leads to this. Great. So now what do we do? I mentioned all of these problems, and all of these problems, when we look at them from a higher perspective, leads us to the greater problem that is how to approach sustainable architecture and construction. This is something that is called a wicked problem. Have a look at the research done by Horst Rittel. It's really interesting. A wicked problem is a problem that does not have one coherent solution. Also, all of its parameters are sticky. One changes, the other changes. And sometimes they're contradictory. In order to solve one, you need to do the exact opposite for the other. And so architecture, its design, its fabrication, its automation processes is this wicked problem. How do we even begin to tackle it? This is the ecosystem that Shiliu and I come from, and also Fanas. We were educated to think about co-design. And the research at the Cluster of Excellence in CDC, part of the Stuttgart University, brings together different research resources and institutes to try to think about the same wicked problem from different directions. So how do we automate? How do we think processes, methods, systems? Our research projects always entail multiple partners that look at the same problem and try to assess it from different perspectives. It starts with material design. It goes on to geometry design, the fabrication processes that we design, the tools for fabrication processes that we design. And at the edge of this design to fabrication process, how do we bring humans into these processes? And so our projects, as I mentioned, explore all of these. Anything from geometry to fabrication processes. Most of our work through the years was done by design demonstrators, pavilions of different sizes. And currently we're working on our largest scale demonstrator, a full building scale, a huge full building scale. But this is not the only way we explore these wicked problems. We also assess it from computational methods. So anything from optimization processes, specialized algorithms, BIM, how do we inform fabrication and design systems that are already existing in the market and how to do that? And of course, our heroes for this one, robots. So we are still believing that automation processes have a lot to give and have a lot of potential and could potentially solve these problems of, first of all, this knowledge that is missing, and second of all, these production levels that we should meet. And we have different types of methods of approaching robotic fabrication. On the bottom right, you see research on CRC, on small-scale swarms of robots working together, fully automated with the exception of the operator. Bottom left, you see the very large-scale industrial arms working in a factory-like setting, but unlike the factory-like setting, these are more in the wild. You see that they're not separated by barriers and workers work closer to them. On the top part are cobots, collaborative robots made more safe towards collaborative processes. We had another discussion at the ACC symposium last week if cobots really exist, because in order to actually achieve collaboration, we need to do a lot more. Cobots are not collaborative per se. You need to arrive at that situation and design all of the tools and processes around them. But they're safer, they're smaller, they have all these lovely sensors in their body, so we can physically stop them, we can manually program them. That's easier for the end user, and that's very important for us. A little bit about human-robot collaboration. So when we're talking about design research in this one, our motivation is to think about processes, end users, and products. We spoke a little bit about Industry 4.0. I didn't explain to you why we moved to 5. And the reason why we moved to 5 is because of human centricity. The idea of fully automated processes, in a sense, failed. It failed because it wasn't real to begin with, because there are always operators around and there are always workers at the edge of these processes, specifically for the construction and prefabrication industries, because a lot of the wisdom that is there is by humans, and a lot of the decisions that are made sometimes have to be made on the fly, and robots are not good for that. Humans are excellent for that. So the new push towards Industry 5.0 is talking about a sustainable, resilient, and human-centric fabrication because of all of these reasons, because robots are resilient and adaptive, and strategically speaking, we can take our businesses and change it in size and scope when we have automated methods that are already perfected. On the sustainability part, we have circular processes, we have reduced waste and emission, and reduced energy when we have controlled and cleaner processes. And then on the human centricity side, we have our own intelligences, knowledges, problem-solving capabilities, and also things that maybe you don't imagine are problematic in human-robot collaboration, but communication is key. We're great at this. They kind of suck. And we need to find the middle ground between the two of them as very different agents in a collaborative system. So human and robots, I already touched upon it a little bit, but professional experience, intelligence and communication, problem solving on one hand, productivity, worker safety, a lot of these processes that are in fabrication and construction, there are so many dangerous processes or processes that could over time hurt your body, like heavy weightlifting. Also, other types of menial tasks that just take a lot of your energy during the day. And so robots allow us that, but they also allow us interconnectivity. We can connect with or interface with different tools coming from 3D modeling, for example, so bespoke fabrication. We can connect with different entities and say, inform our robot with sensors, with cameras, communicate whatever these learnings are to other systems, and then operate parallel processes at the same time. What else did I want to say about humans? I had another point. Important to say, maybe I'll get back to this point in a second. So maybe to show you some examples of what human-robot collaboration with cobots look like. So this is from our lab in Wangen. This was an experiment that I will later talk a little bit more about. But in this experiment, as you can tell, the user and the robot are sharing the space, but they're not sharing it at the same time. So there are ways to interact very closely with robots, responding to different temporal and spatial arrangements where you can keep safety. This is also very slow. We will touch upon this later because humans being humans, we have different preferences as to how we like to work together. Another example of working with cobots, I mentioned that these are safe and could be manipulated by hand. This process is called learning by demonstration. So you could potentially move the robot around, either in simulation, what you see on the far right, or in real life, what you see in the middle, record their track and use it either physically. So this you can do with a robot's pendant, and this is how a lot of the processes are done in a factory line or whatever bespoke fabrication, but also as a data set for machine learning, for reinforcement learning algorithms to be exact. So you're using this information as a way of teaching the robot and getting it to arrive faster as something that's called generalization, how to respond to changing conditions. I want to start with this project that I actually did outside of ICD. I love starting with this project because, first of all, it's super fun. And second of all, it was my driver, in a sense, to go back to academia. And I'm going to prompt you a little bit, try to do things differently. I was very, 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 very lucky to join this team at HAN Studio B Berlin at the time. And we were working on a design installation for Make City Berlin. That's a festival for architecture making. And in this one, we were invited to design what the future factory would look like. And we said, okay, Industry 4.0, that's how old I am. Let's bring everything to the architecture firm and have a design to fabrication to assembly process on site. This is what it looks like from inside our augmented reality interface. So the idea was this. We got a couple of ABB cobots in-house with hot wire cutting, like the students are doing right outside. And we can manipulate the robot on demand with hand gestures, and we can manipulate the design also on demand with hand gestures, and even receive assembly instructions all through the same interface. This is what it looks like from the outside. We invited a bunch of architects, their families, their kids to come play with our design. I mentioned the connection to Industry 4.0 before, so I'm just going to jump ahead. We use Rhino and Grasshopper and Hologram, your neighbors from Melbourne, to communicate between the robot, the design interface, the fabrication area. And so our hand gestures could manipulate the interface. Our voice recordings were used to design the facade. So every person was invited, recorded their voice, and then created different facades. And then just flicking around inside the interface, you could move between design to fabrication to assembly modes. You've seen these projects before. I mean, it's 2025. You've seen these projects before. This is one interface for sound. This is what the facade looks like once you record it and sent it and send the file for fabrication. And I think what was really cool for us at the time was to think about interfaces in the same way that we think of buildings. So what is the new role for an architect in the 21st century? Is the design of processes where others participate, is to give other people space, but maybe it's a digital space. So some of the limitations as architects were think about a component that fits your hand, or think about a size that, the shortest person in the room, being Germany, that was me, could assemble. This is the physical space where we practiced and tested it. And you see that we already pre-assembled some of the rows as the base of the design. And this is the digital space that was happening concurrently. So you could shift between the digital mode and the physical mode. This is what it looked like. Another thing that we wanted to challenge ourselves in this design was to say, okay, we don't know what the end product is. Let the user play with it as far as they want. And you see these funny anchors at the top of the building. You could push and pull them and the building would grow accordingly. A lot of fun. This one repeated itself. So on-demand robotic fabrication, as soon as you recorded your voice, the file was translated into robotic toolpath and cut by hot wire cutting. And it also took care of the angles on how to assemble it. And you got your assembly instructions. Take this, rotate it, go back to the structure, place it in place. Very cool. You see Sakib here in the picture? I'm kind of fronting you towards this question. Who was this designed for? The person. I mean, we hope so. Yes. You can imagine by the previous one who did most of the assembly. So why is this funny and also very true? We made a lot of assumptions as designers. We thought that this would be easy peasy, accessible, amazing. And we invited, as I said, people who work with technology and people who don't. And the most part of their time, they actually spend just understanding HoloLens as a space. They also noticed that it didn't match them all that well, depending on the different bodies. And also they were bombarded with information. We couldn't get everything we wanted at that time. As a person who also spent a lot of time inside the HoloLens in this project, I could tell you that this building where we were has a concrete core. So every time we pass by it, the connection to the HoloLens would be disrupted and then we would lose all of the simulation. Also, it was HoloLens 1, so there were discrepancies between the actual building and where it should be overlaid. It was highly inaccurate. Also, it's a pain wearing this for so many hours. It's not a fun feeling. It's not cool to work with. And it's fun and really, there's something liberating talking about design from all of the perspectives where it doesn't work. Because usually as architects, we have the tendency of showing a perfect render and say that everything's amazing. And it's not. And it's okay that it's not, because this is where, I guess, simulation or render starts and real research work begins. We need to work towards what's not working. Why is feminism related to that? Do you know?
Well, a lot of these systems are designed by men, right?
That's a really good point. That is also true. So when you have people like us designing for people like our own selves, we designed it for other architects who are nerds and love to play with technology. There is also the adaptation or the lack of it to different bodies, for sure. When I was testing the previous test, it was calibrated to my boss, Giovanni's voice, bass. And whenever I recorded my voice, it just didn't work. And it wasn't until I was looking into other people's like ideas of what human robot collaboration from academia to the practice look like, that I realized that actually we all make these assumptions a lot. And these are beautiful research projects, some of the most known in the market or in research, but they stay on the shelf. We cannot say that we design for the practice if we really don't test with the end user. And so the first thing that I did coming to this research was try to inform myself what was there, what was working, and what was not. I feel like jumping to the next slide because I mixed up the order. So I want to talk to you first about this. Feminist critique, or specifically feminist critique of technology, that's called feminist technoscience, is nothing new. It's been there since a while, and it really peaked from the 80s on. Why it's interesting to human-robot collaboration design, human-computer interaction design. On the screen are the Barzells, Shawan and Jeffrey, Lucy Suchman, the queen of interaction design, Catherine D'Ignazio and Lauren Klein, and Daniela K. Rosner, who approach design and datasets of design from what are biases in datasets and biases in design, the origins in design, who should be getting more credit for the work in the design space. And also I hear there's a beautiful exhibition now in Sydney from Kate Crawford, Atlas of AI. She's absolutely relevant for this conversation. So all of these thoughts about how to design interfaces, for whose body, for whose purpose, how readable are they, and super important, how well do they actually give you information that is right now happening between the machine to the human and what's in between. This is Suchman's work, by the way. Back in the 80s, this is what she did. She was noting everything that a Xerox machine was doing, and then she was noting everything that the team of 3 people, one mathematician, one Nobel Prize winner and herself, like not silly people sitting in the room, could not fathom, because the beginning of interface design was just an assumption, and you need to meet people halfway. And Donna Haraway is, of course, there because of her cutting edge notions about how technology augments the body, and later on how technology, body, like humans and environments, are equal actors. This relates also to Bruno Latour, talking about Ant, but I'll keep it at that because I want to show you some projects. So I prompted you with this idea of design, but what did I take from it? When we're designing interfaces and human-robot collaboration interfaces, what I realized that was super important, what I realized was super important are 4 main concepts. And these 4 main concepts are formed as design generators, but also as ways to review design and see if what we designed is actually where we want it to be. We start with embodiment. And embodiment, we talked about the body, we talked about the perception that comes with the body. We haven't yet talked about safety and physical actual safety, and also the perception of safety, which are 2 different things. If you feel safe, if you feel you have trust to the machine, then human-robot collaboration will be successful. If you don't, it's null, it's not working. Reconfiguration talks about augmenting the user, augmenting it with additional tools, augmenting it with additional accessibilities. It could be the IoT that you're relating to. Hello, guys. And it could be the additional tools that are added. It also means that sometimes there are dependencies between humans and technologies. What does it mean? Let's, for example, think about our phones and how agitated we can be just thinking about that beep that we heard. So we form these connections between technologies and bodies and perception and state of mind that are very important to pay attention to, because if we're designing for a person working 8 hours, all of these make or break the routine. Interrelation and participation. So I guess I covered reconfiguration and interrelation at the same time, but maybe this image is a bit better for interrelations. So do the tools and sequences match the site and task? We can't only design for the demonstrator. We need to design for the actual thing and the actual people. Do the tools and sequences help solve real problems? In the previous example I showed you, we created a problem. What about the real ones? Is this the real material? Is it representing well the construction site? I worked in that specific project with HoloLens. Can I work with the HoloLens here? We need to consider all of these things. And then can the tools and sequences adapt to changing conditions? Let's say that I wanted to work with that HoloLens. What happens when light is occluded? What happens when a user is just physically different or is wearing very thick glasses? All of these are parameters that relate to our design. And the workers, the people at the edge of this process for which we're actually intervening for. Do they match the workers, the current ones, the future ones? Processes, technologies, and businesses change over time. Can our tools that we suggest adapt to the different user? And also, well, we talked about diverse bodies, ages, genders, cultures, needs. And the final and most important, I want to talk about participation. This is not synonymous with our research work. It is with ours, and Shirley will show her part later on. But for us, it's super important to include people in the design process as it's happening, and in some cases also as design generators, because it changes everything. And sometimes in academia, we just want to engage with something that's new and exciting. And we ask a lot of good questions, but we forget to ask, what is absolutely annoying that needs to be automated? Does it make sense? Super. So bringing you to, let's see how well I am with time, bringing you to my design space. So this is composed of 3 parameters, which are participation and feedback. Every single design exploration that I do has participation and feedback to it. Reconsidering task distribution, this will be what we're talking about, and using new technologies for that. And I'm going to show you some examples from our research at the ITEC program and ICD. So how to design HRC for uncertainty and diversity. Uncertainty in this context is all of these conditions that change. Site conditions, material conditions, and changes in the environment. It could be, we work in a fabrication area where different machines are constantly moving, where different people are constantly moving. When you turn a machine on and off, there's enormous sound in the space. If I'm working with microphones, for example, it affects it. So first example, this one is called Deep Agency. My ITEC students 3 years ago already. I showed you, I will talk about this one. Usually when we think about human-robot collaboration, the division between the different agents who participate is that humans do dexterous manipulations and they move around, and robots do something that's kind of repetitive, has to do maybe with force, and pre-decided, so like hard-coded. In this one, we wanted to challenge this regular divide and say, okay, let's think about a regular problem, timber joints that are very, very narrow, and give the dexterity this time around to a robot. How would we do that? We compared different methods of collaboration. You see here, Salvi, Celine, and Pengfei. And what they're doing is by hand manipulating a robot so it could properly insert a very tight timber joint, a lap joint. You see it in the video in the middle. And then this one was compared into that same action manipulated in digital space. So basically in a physics simulation space. And the registration that you see happening on the left is informing a simulation that is later input as a part of the robot's trajectory. So the robot itself would know how to jiggle about and maintain these motions that are a bit human-like. What you can also see, if you notice from the joint in the middle, is that physically manipulating an object like this one is actually quite hard. If you worked with URs before, you know that they're very hard to move. A part of the learning of their simulation to the left is that the physical manipulation was not as good. Actually, they had better results with their algorithms and optimization when they manipulated the robot in simulated spaces. And so the use of demonstration for optimization and a neural network as a mediator for accurate performances that otherwise would have been done by a human. Another example of this like divide between human and robots and what they usually do. In this one, we were thinking about how a robot could become an assistant, an active assistant in an action that is not pre-programmed. And this action that is not pre-programmed is processes of disassembly. With my students and I, and also the co-tutor for this one is Felix Amstveld, we were thinking about why construction disassembly is not being automated. And there are very many reasons for it. First and foremost is that this is a very uncertain environment. You don't know which component is coming out next. You don't know how risky this is. And also, it's hard to bring robots around to the site. So we were trying to imagine a demonstrator that would use these parameters. And we were trying to imagine the robot as an other that assists you in these processes. So using physics simulation, wait, this should be running. Whoops. Okay, I'll show this and then I move to the next. Using physics simulation, we were teaching the robot in advance what would be possible sequences of disassembly. And the reason for physics simulation is because once you take an object that is not intuitive to take out of the system, the whole system crashes. So basically the robot learns on its own how the system would behave in a world that has gravity, and then proposes additional solutions to the user. So we have different agents inside an ongoing system that propose to you different things, which object to take first. They also communicate with an overall manager, and then they communicate with an LLM that physically speaks to the user as if it was another person in the room. And the QR codes or Aruco codes that you see is for an additional system that could track where exactly the robot should approach and collect the components. And I think I'm just in time to tell you about a last project. So I'm jumping forward a little bit because I want to talk to you about a collaboration that us at ICD and ICDCA did with the Institute for Social Sciences. This is very much around working with carpenters. And here we had a bit more time and an ongoing collaboration with a company called Muller Blaustein. And so we could invite them into the lab and to assess processes of human-robot collaboration design. To prompt you a little bit about this, the idea was, oh, I'm sorry, this is what I wanted to show you. The idea was how to enable easy access interfaces for on-demand communication and control over a robot. And thinking about the end users, they don't code. Most of them haven't worked with robots before. Sometimes working with a pendant doesn't make sense because you need to concurrently use another tool because you have tools that you're working with. Sometimes the environment could get super loud. So you need to think about alternative ways where you can collaborate with a robot. We came up with this idea of introducing hand gestures instead of a regular communication with a robot. No, and not coding, not pendant. And then we were being a little bit cheeky. We thought about this demonstrator that's Jenga-like. And the idea is that one person, like a person assembles one block, the robot assembles the next one. And we gave them a task, do this as accurate as possible. I said we were cheeky. If you can tell, the units we gave them are not equal in size. So if they're not minded, and if they don't manipulate and correct the errors, the tower is either not stable or collapses. We were also cheeky in the sense that I'm saying the cheekiness I did. So sorry for that. We were also cheeky in the sense that I hard-coded errors to the robot. I wanted to see how people respond when the robot actively crashes into the structure. I wanted to gauge and understand all of the responses that it brings from them. And once I get the feedback, to design for that. We compared two different conditions, one with a robot that is non-responsive, so it doesn't sense, it doesn't respond. It's just like a deaf, dumb, and blind robot, like the Who's album, and another one that is acknowledgeable of its environment, of its user, and responding to force torque sensing, to motion sensing, to depth sensing. Am I leaving anything out? That's about it. These are the users. And this is what the collaborative process looks like. So very close. Some of these people haven't worked with robots at all, so it was a first encounter. We invited them to the lab, we let them sit, understand the rhythms, understand the sounds. Working with a robot has its own sounds, and understand the failures. And we counted every single time a failure was happening. This is a hard-coded failure. And this I didn't expect. So when you invite people in, you realize so much more about humans that you don't know. For example, people who don't work with automation assume that automation is actually wiser than it is. They don't foresee an error, and they attribute a lot more intelligence than should be. When this happens, they also have a tendency of not paying enough attention to their own bodies in relationship to the robot. They should be a lot more scared than they are. We compared this crowd to a crowd of researchers, PhDs, master students who work with robots. Who were the most scared in the room? Absolutely. They thought we were insane. They didn't appreciate being so close to a robot. They didn't like that the robot was inaccurate. They hate the sound when something was crashing. They were terrified. And I love having these two populations in the same room because I'm getting completely different views, and I realize that at the same time I need to have both in mind. I need to have the care that PhD researchers have and their knowledge and wisdom, and I need to think about people who will be absolutely not knowledgeable of this and will put their body at risk. I showed you a little bit about this interface. This is what it works. This is how it works. So we gave them very easy to use hand gestures to control the robot motion and the gripper motion. Remind me about this one, I will tell you how it's biased. And then a move between design to simulation. We actually did this one twice. So one was using Rhino Grasshopper as a mediator and the simulator. The other one is just full on Python. And this is what the digital and physical space look like. So on the right-hand side, you have what the robot sees. You have a depth camera that's mounted on the flange. That's the 6-axis right here. And it's looking towards the tower that's being built. Whenever a human approaches and places one brick, the robot acknowledges and places the next one. Also, it's noticing when the hands are moving in that same environment for safety. So as soon as a person is close to the tower, it stops. On the left-hand side, you have my view of the human-robot collaboration. I'm sitting on the side and monitoring, and an additional camera for the hand gesture. For hand gestures. And in the middle, you see the environment. So there's a lot of tech in this teeny tiny thing. There's an interface. You see that green arrow over there? This is an interface for the user. What I did in this one is I compared two modes. One where the robot is looking at the person and responding, kind of having more agency. So the robot is using all of these sensing to stop, to go, to make decisions about assembly. I compared it with another condition where the human is operating and using hand gestures. So in this one, the robot is only responding. And you see on the screen on the right-hand side, what the human was seeing as well, what the user was seeing as well. And then we ran a third variation, everything combined. Guess what happened?
Yes.
In what way?
You have different senses, different actions, so maybe simultaneous actions would be accurate.
I love it. That was absolutely what was happening, and all of the chaos that I thought I can expect, there was additional stuff. So when I had architecture students in the room, they were absolutely fascinated by the robot, of course. Oh, wait, I'll show you the next slide. And so the horrible results are architecture students. They did not pay attention to the task at all. All they wanted to do is probe the robot and try to understand how it works, when it works, which kind of gives you a hint towards when you're inviting people into the lab, it's actually a very good thing to let them play a little bit before, get all of that playfulness out of them, and then possibly tell them, okay, you have a task, you need to finish it after so-and-so. Or you have a task, and maybe if you succeeded, if you complete it under this and that time, there's a prize. Because otherwise they're going to, it's their fun time also. They're seeing tools they've never seen before. On the left-hand side, stakeholder performance, these are the carpenters. But this is from the previous test. So the carpenters were consistently better at what they did. But sometimes they didn't use the tools at all. When there were multiple interfaces to interact with, they didn't appreciate it because they needed to concentrate on more than one thing. So you have the robot in front of you, you have another screen, and then you're supposed to remember the hand gestures, which we thought would be intuitive. It's not. It's very confusing. I told you to ask me about the hand gestures, so I'm going to prompt and tell you about it already. These are my students. They're lovely. They're very much like me. They like robots. They're also very much like me in the sense that they have smaller hands. Carpenters have far larger hands. And it wasn't until I tested it with 30 people that I realized that the algorithm I'm using with my camera is biased, and it didn't detect bigger hands. So there's so many parameters to consider when you're using this like instrument heavy process. I mentioned Ant before because when Latour is talking about processes where technology and humans are equal agents in the system, I'm thinking about it from the way of which is responsible and where something fails. Because something could fail because of the camera, something could fail because of the operator, could be my mistake. Something could fail because I forgot to turn something on, or the cable is failing. And it's really interesting to think about these systems because all of them have almost an equal effect on success or failure. Yeah, I think, so I'm happy to show this because over time, like these are results on the left from the first user study. This is the second. Definitely there was an improvement, but what I'm working on at the moment is an improvement on how I visually speak to users because my interfaces were interfaces for a nerd that knows the system. If I would use it for the first time, it's way too much information. It's not readable. It's not accessible. So with every design iteration, I get feedback from my users. I also think about it myself, and it leads me towards the next one, which is, I think, was a lot of information, but maybe a good point to kind of like rest and say, okay, this is a space where cutting edge technologies, task distribution, participation, and feedback kind of meet in the work that I do. And to thank you for your attention and ask if you have questions. Should I stop sharing?
Good light.
Okay. This was me.
Yes.